So the first thing is the convention to relate the energy moment tensor with the metric variation. I interchange the negative sign. So let me give you the correct convention. So in the hurry yesterday, I interchanged the negative sign. So the correct sign is when you make a variation in the metric, the variation in the action, strictly speaking, it is minus when you have T mu nu delta G mu nu root minus G d4x. So earlier, I had used positive, actually it is negative, and the other way around it is positive. Obviously, that can be shown is 1 over 2c. Okay, and with this is the correct convention, and with this correction, yesterday's Einstein equation that I obtained from the Einstein-Hilbert action, it is actually plus 8 pi g c4 T mu nu, provided of course, as I had defined, R mu nu is, with this, yesterday I was getting negative sign because I had interchanged the signs. So with the correct sign assignation, you will get this as the Einstein equation. The first thing. Right, yesterday what we saw was when you make an infinitesimal coordinate transformation, where old coordinates go to new coordinates generated by an infinitesimal coordinates transformation via a vector field. It's infinitesimal because the absolute value of epsilon is much, much less than unity. Then we saw that the new metric G prime mu nu as a function, so we saw that G prime mu nu as a function now. So I will not use x prime or x, it's a function of a variable. That variable I am using x, we saw is nothing but G mu nu as a function of the variable x was plus epsilon xi mu covariant derivative nu plus xi nu covariant derivative mu. Towards the end, I asked you, I had got an expression. So I asked you to, there was one step missing. When you fill that step, you get this expression. Okay. So in other words, in general, xi mu is an arbitrary vector field for any arbitrary vector field that is, of course, differentiable. You find that under this infinitesimal coordinate transformation, your new metric as a function of the variable x is equal to the old metric as a function of the variable x plus this term. Therefore, if you want that your xi mu generates a space-time symmetry, meaning what? That when you do the coordinate transformation using this xi mu, your metric as a function doesn't change. So if there is a space-time symmetry, if xi mu x generates a symmetry. Meaning thereby that the new metric function is the same as old metric function. So this is equivalent to G prime mu nu of x is same as G mu nu of x. This is the meaning of space-time symmetry. This can happen only if xi mu semicolon nu plus xi nu semicolon mu is 0. That's the killing equation. So obviously, whenever there is a symmetry, something is conserved. That we know from our classical mechanics days, and this is true even in quantum theory. Even in quantum theory, whenever there is symmetry, there is a conserved quantity. And in quantum theory, you know what is the condition for some quantity being conserved. Condition is whenever that quantity as an operator commutes with the Hamiltonian, that quantity is a conserved quantity. It also follows from the symmetry. Now we will show that indeed whenever there is a killing vector, there is a conserved quantity. Now we all know that if you have a particle, test particle, freely falling, then the test particle's free fall is described by the geodesic equation, and the geodesic equation can be cast in many forms. One of the forms that probably Bhaswati did was that if x mu is parameterized by the lambda as it is falling, then it satisfies the equation d2x mu by d lambda square plus gamma mu alpha beta dx alpha by d lambda dx beta by d lambda equals 0. That's the geodesic equation. What I showed was that if you have the tangent vector for this freely falling particle u mu, which of course is dx mu by d lambda, then when it is going along the geodesic, the tangent vector is parallel transported along itself. That means d of u mu by d lambda is 0, which is nothing but u mu semicolon nu, u nu is 0. By the way, this is equivalent to the geodesic equation that we showed in one of the classes. The same as geodesic equation, except that u mu is the tangent vector dx mu by d lambda. Okay. All right. So we have a particle which is freely falling, and thereby it is satisfying that equation, which is also true in local inertial frame. By the way, these are all in local inertial frame. A freely falling particle, what equation does it satisfy? In local inertial frame, no force is acting. So d2x mu by ds square is 0. And local inertial frame, gamma mu alpha beta is 0, and you get back your usual. So everything is consistent with Einstein equivalence principle. Now, in curvilinear coordinate system, see, in special relativity, we talked about 4 momentum. In special relativity, 4 momentum is rest mass into speed of light in vacuum into dx mu by ds, where ds is square root of eta mu nu dx mu dx nu. So accordingly, the 4 momentum in curvilinear coordinate system, p mu is also mc, where m is the rest mass, dx mu by ds. The only difference is x mu is the curvilinear coordinate system and ds is square root of where mu and nu are being summed over. This mu is not summed over, so you could have called it g alpha beta dx alpha dx beta. This mu is free, it's not being summed over. Okay. So this is your 4 momentum in curvilinear coordinate system. So it's also true for curved space-time. In other words, this can be also written as mc into u mu. Because u mu, I mean, you could have parameterized the geodesic in terms of the proper distance s. In general, you can use any affine parameter lambda, but you can also use the proper distance to parameterize a geodesic. Right. Therefore, we ask ourselves that here is a particle which is freely falling, p mu is the 4 momentum, and it so happens that in this curved space-time you have a symmetry. So suppose there is a symmetry. That means what? So suppose you have a Killing vector. So suppose xi mu of x, a Killing vector field, characterizes a symmetry of the space-time. And you ask the question, is there a conserved quantity? That's the question we are asking. Now consider the following scalar. Okay. What is the scalar we are interested in? Take the 4 momentum p mu and contract it with xi mu. So I am giving you a space-time where there is a symmetry characterized by the Killing vector xi mu. Xi mu is a vector field. The p mu, 4 momentum, is a vector. So therefore you can use the Killing vector and contract it with the p mu. It's a number, it's a scalar field. And ask, as the particle is freely falling, along the trajectory, what is happening to this scalar quantity? How is it changing? What do? You say d by ds of this quantity. Okay? All right? Now, this is a scalar. d by ds, so this is very important what I am going to say. d by ds by definition from the chain rule of partial derivative, by definition, what is this quantity? It is del by del x alpha of p mu xi mu into dx alpha by ds, pure chain rule partial derivative, just mathematics. Agreed? However, we also know one thing, that p mu xi mu is a scalar. Ordinary partial derivative of a scalar quantity is same as covariant derivative of the scalar quantity. We have already done it, that for a scalar field phi, covariant derivative of scalar field is same as partial derivative. Because parallel transport, how did we get the notion of covariant derivative? The notion of parallel transport. An object which is just a number, that number remains the same when you parallel transport. Vectors have components, so that's the reason why I had to introduce Christoffel symbol to check how the component values change when you parallel transport object. Hence, this object can also be written as p mu xi mu, ordinary partial derivative with respect to alpha is same as covariant derivative alpha. Dx alpha by ds is the tangent vector u alpha. P mu is mc u mu, so the mc can be taken out, and this is nothing but u mu xi mu u alpha All right. Now I know that covariant derivative is a derivative. Leibniz rule must be satisfied. So therefore, this will be MC. First, u mu covariant derivative xi mu u alpha, and then plus u mu xi mu semicolon alpha u alpha. Okay. I will now rearrange. After all, we are not doing quantum mechanics. We are doing classical physics. In quantum mechanics, we deal with operators. So you have to be very careful rearranging, because in general, operators do not commute. But classical physics, you can interchange the order, and therefore this is same as MC u mu alpha u alpha xi mu plus xi mu semicolon alpha u mu u alpha. I have just changed the order. But u mu semicolon alpha u alpha is 0 because it's freely falling particle. The tangent vector is being parallel transported along itself. So the first term is 0. So therefore we have the result that this is 0. But what about this quantity? Xi mu semicolon alpha u mu u alpha. Note, u mu u alpha is a symmetric second rank tensor. U mu u alpha is same as u alpha u mu. Xi mu semicolon alpha is antisymmetric, and we all know a standard tensor calculus result that if you have an antisymmetric tensor and a symmetric tensor, this is 0. Why? This is very simple. If it is antisymmetric, this is minus nu mu. This is symmetric, so this is plus nu mu. But nu mu, there is a dummy index. Nu I can just interchange. I could have written it as S mu nu. Whatever I am calling nu, I will call mu, and vice versa. But anything that is negative of itself is 0. So this goes to 0. I will apply this general result in this particular case, that xi mu semicolon alpha is an antisymmetric tensor, u mu u alpha is a symmetric tensor, and mu and alpha are being summed over, so that is also 0. So this is 0. And hence we have got the result that if there is a killing vector, the scalar quantity p mu xi mu along the geodesic doesn't change with time, because this is 0, strictly 0. So hence p mu xi mu is a constant of motion. So as an application, there are many applications. As an application, whether as Anuj did with Kerr black hole or Schwarzschild black hole, you can immediately identify two conserved quantity, namely energy and angular momentum. For example, in the case of Schwarzschild black hole, if you take the Schwarzschild black hole, so there is a constant of motion. In the case of Schwarzschild black hole or Schwarzschild space-time, need not be a black hole. Your G00 is c square 1 minus 2 gm c square by r. No, not c square, just this. And it doesn't depend upon time. And none of the metric components depend upon time in the Schwarzschild space-time. So 1, 0, 0, 0 is a killing vector. But someone must show that it satisfies the killing vector equation. It does. Take it as an exercise to show that in the case of Schwarzschild space-time, xi 0 equal to 1, xi i's are all 0 is a killing vector. Okay. It's obvious because the metric doesn't depend upon the time coordinate, but you can show that this vector indeed satisfies killing equation. And therefore, if you contract, so take the xi mu, this is the time-like killing vector, xi mu being 1, 0, 0. Similarly, there is another killing vector you can immediately identify. The Schwarzschild metric components don't depend upon the phi coordinates. And therefore, the other killing vector we can immediately identify is xi mu phi, which is phi being the third coordinate, so 0, 0, 0, 1. And therefore, for the Schwarzschild space-time, this quantity P mu xi mu t, which is nothing but g mu nu P nu xi mu, and because xi mu t has only the 0 component non-zero, this is nothing but g0 nu P nu. And for the Schwarzschild space-time, the metric is diagonal, so nu is being summed over, so only G00 will come, P0. And G00 is 1 minus 2gm by c square r, and P0 is mc dx0, so mc squared dt by ds. This is a conserved quantity, and it can be identified with the energy divided by C. Okay. All right. So, any trajectory in the Schwarzschild space-time which is freely falling, remember, is a constant of motion along the geodesic, is a constant of motion along the geodesic. So any freely falling particle in Schwarzschild space-time, the energy is 0. Yeah.
Can you briefly repeat the parameter, this different parameterization, affine and non-affine parameterization?
For the trajectories. Yeah. So we are saying affine parameter. I should switch to right hand. Suddenly found that I'm slow with writing with my left hand. Yeah. So okay. So affine parameter is just a real number parameter to describe the curve, because we have seen a curve is a mapping from the real line to the manifold. Okay. So therefore, when you have a mapping from the real line to the manifold, you give me one value of the real line, I will tell you which point in the manifold I have. So in particular, x mu for a curve, any curve in your manifold, now the manifold is being described by a chart, so it has coordinates. So therefore, you tell me, give me a real number lambda, I will tell you what is the space-time coordinates. But someone will ask, what is this lambda? The fact of the matter is, for any curve which is one-dimensional, you can choose any parameter. Where this is a one-dimensional object, I'm free to choose any parameter. So as an example, suppose in a two-dimensional plane, I want to describe a circle. Circle, I know, if this is the radius a, circle is x square plus y square equal to a square. So the curve, namely the circle in this case, has the equation x square plus y square plus a square. Here I am not defining the curve in terms of any parameter. Okay. But someone will say, well, you know, it's better to describe the circle, which is a curve, in terms of parameter. So I'll say, okay, let me choose the following parameter, that I will say x is equal to a cos of t and y is equal to a sine of t. So t is my parameter. Indeed, this describes the circle, because if you square it and add it, you will get a square. But someone will say that, no, I am not happy with the parameter t. For a object rotating with a angular speed 1, there is a physical significance of this. An object which is rotating with the angular speed 1 will have this equation actually. In general, if it is rotating with angular speed omega, someone will say that this means your particle is, if t I interpret it as time, someone will say that, oh, your particle is rotating with angular speed 1, why should it rotate with angular speed 1? Someone will say, no, I will choose the parameter omega t. Then you will say x equal to a cos omega t, y equal to a sin omega t, and indeed, then I can interpret t as time and omega as the spin angular momentum. Someone will say, well, that's one parameterization, but why not I choose some theta square as my parameter? That's also valid. So ultimately it boils down that the circle's equation x square plus y square equal to a square, the same equation can be described by infinite number of affine parameters. So the parameter which is arbitrary, normally in tensor calculus we call it affine parameter. But there is a special parameter for particles that move with speed less than c, namely the proper time parameter. Proper time parameter cannot be used for null geodesic, because for null geodesic ds is 0. For null geodesic, the parameters are arbitrary. That's why I have been using d lambda in general, because for null geodesic, the tangent vector, you can't use dx mu by ds, but ds is 0. Proper time for a particle moving with speed c is 0. You have to use the arbitrary parameter. I hope I have clarified the question.
Non-affine parameter means?
Well, I don't know what is non-affine parameter, but I don't know. Yeah, one has to see what do they mean technically when they say non-affine parameter. So we have proved that if there is a Killing vector field, then along the geodesic there is a constant of motion, and we found that if you apply it to freely falling particles in the short-shelled space-time, this quantity is a conserved quantity, and this is what is E. So in particular, you can say that if a particle, due to some reason, as it is falling, I keep on drawing away its energy. It's freely falling, but I keep on drawing energy. How much energy can I extract before it crosses the event horizon? So you therefore check that I started with a particle from infinity at rest. The particle at infinity from rest will have energy what? Rest energy, mc square. But as it freely falls and I keep on drawing away its energy, once it comes close to the, now I am talking about black hole. If it comes close to the event horizon means your radial coordinate now is very close to gm by c square plus epsilon. You can't reach the event horizon as seen by an observer at anywhere else. This epsilon is, so you're very close to the event horizon. Then, how much energy you have, or rather you are asking the following question. When it's very close to the event horizon, what is its energy? Okay. How will you get it? Remember, the conserved energy at any place is this. But you will say that, how do I find out what is dt by ds when the particle is very close and it's almost at rest? How do I do it? Very simple actually. When it is almost at rest, ds is square root of all those g00, etc., etc., etc. But when it is at rest, the spatial part is 0. So when it is at rest, it is simply g00 c square dt square. Okay? So it's same as square root of g00 c dt, and therefore c dt by ds. So therefore your conserved energy when a particle is almost at rest near the horizon, the energy of the particle E by c is nothing but 1 minus 2 gm by c square r mc c dt by ds, because it is ds is c dt, I have proved. C dt by ds is 1 over square root of g00. So this energy E by c is for what? A particle which has come almost at rest near the event horizon. Rest near the event horizon. But square root of g00 is, g0 is just 1 minus 2 gm by c square. So this is square root of 1 minus 2 gm by c square r into mc. And therefore the energy E of the particle which is just near the, at any point, because this r is still a variable, so any which has come to rest at any radial coordinate r, this energy is square root of 1 minus 2 gm by c square r into mc square, because E by c was this. Is that clear? So let's look at what I have done. What I have shown is the killing vector told me there is a conserved energy. Now I am saying, suppose I drop a particle, just drop a particle from infinity. At infinity, there is no gravity and I know what the energy is. A particle at rest at infinity has only the rest energy mc squared. Now it is freely falling. As it is freely falling, I am constantly extracting out energy. Then it comes almost at rest at radial coordinate r. Then I have proved for you the result that its energy is this much. Okay? Agreed? Does it make sense from Newtonian point of view? The answer is yes, because its energy is less than mc square, and the division, if you subtract out, is exactly the gravitational potential energy. But my question is different. What is the maximum amount of energy you can extract? R, if it is event horizon plus epsilon, then it is nothing but, by the way, I could have written 1 minus event horizon radius by r. So this is like 1 minus rs by r, and r is rs plus epsilon. You can see into mc square. Okay. As epsilon tends to 0, the energy tends to 0. So that means I can extract its entire rest energy if I make the particle fall, almost reach the event horizon. In fact, this is the principle behind quasars. You know, when quasars were discovered, quasar was Martin Schmidt, right? He was a guy who the first quasar was discovered by him. And when quasar was discovered, people found that quasars emit humongous amount of energy. Okay, 49 ergs per second, humongous energy, and yet they come from very compact region. The quasars appear like a point object. The quasi-stellar, that's why the name quasar came from the word quasi-stellar object. They look like stars, but they are not stars. The redshifts are very large. So they are compact objects, and the energy output is close to 10 to the power 47 to 10 to the power 49 ergs per second. How do you generate such an energy? So there were a lot of theories. Finally it turned out, work from Salpeter, Lynden-Bell, Martin Rees, Blandford, Begelman. There are many people who worked. Late Professor Narlikar had a different theory for quasar. Anyway, I will not go into that. But today we know that because matter, when it is very close to the event horizon, its energy can be, net energy can be zero. That means it started from infinity with energy mc square, and it lost entire energy almost. And therefore, this process is the most efficient way of generating energy. That means what? Gravitational energy of matter falling towards a black hole is the most efficient process of energy release. And the reason is this, that as epsilon tends to 0, that means if you go very close to the event horizon, your final energy reduces to 0. That means it started with mc square, and when it is freely falling towards black hole, you keep on extracting energy. You can extract the entire rest energy of the particle.
How much time would it take to extract this?
No, the time, the proper time is finite. In fact, I don't have time to do the exercise. All this analysis, because you don't have to solve the second order differential equation. Solve this equation itself is a first order differential equation. Drop a particle from infinity and ask what is the proper time taken for the particle to reach the r equal to 0 of the black hole. The time is proportional to, if it dropped from initial radial distance ri, the time is proportional to square root of ri cube divided by 2gm, divided by gm, proportional to finite time. So if you yourself are falling, you will see within finite time you have reached r equal to 0 singularity. Yes, external observer will not see, so what? That's the black hole complementarity, Susskind's black hole complementarity. I don't want to get into that.
I'm a bit confused. So there is the particle with some finite energy falling into the black hole, and at the event horizon, the energy.
No. Okay. I said that the particle is freely falling. As it is freely falling, you keep on extracting the energy. So it's spiraling in. So the real process in quasar, how do they do this physically? Physically they do by saying that you have a black hole, so point like singularity classically, this is the event horizon, and matter from external source like stars, they have angular momentum. So as the gas is coming in, because it has angular momentum, it can't radially come in. So as they come in, they form a disk around the black hole. It's called the accretion disk. Very far away, any element of the accretion disk, very far away, Newtonian gravity is a good enough theory. It is following a Keplerian orbit. Keplerian orbit meaning the angular speed is square root of gm by r cube. That's the Keplerian speed. Omega is proportional to square root of gm by r cube. But then it forms a disk, but there are viscous forces that makes one small element of the accretion disk spiral in and fall into the singularity. Accretion disk was proposed for the first time by Lynden-Bell, then Martin Rees, etc. The whole class of people did work. Most of it is solved. The only thing where there is uncertainty is what causes the viscosity. Whether it is magnetic viscosity, where Chandrasekhar himself did a lot of work whether it is some other kind of turbulent viscosity, those aspects are uncertain. Otherwise, most of the theoretical stuff as far as modeling of quasars are concerned are known. Now it's all numerical, how to get the efficient way of extracting energy. So I lost interest when it went to numerical simulation. Earlier, my PhD was associated with quasars and radio galaxies. I lost interest when it became numerical stuff. But nevertheless, there is still one unsolved thing, that what is the viscosity which causes matter in this accretion disk to spiral in. That is very important actually, that viscosity.
But how to understand, where this energy is lost actually?
Huh? No, the gravitational energy is basically getting converted to photons, no? Because rubbing, after all, the same thing. Why does a meteor falling, the meteor, a stray small asteroid object, once it comes very close to Earth, the Earth attracts it. Why does it burn up? Where does the energy, burning up energy, come from? It is its gravitational potential energy becoming more and more negative. It started with some energy. That energy, because of friction with the atmosphere, heats it up, just like when we rub our hand, the hands get heated up. So if there is a viscosity, your bulk kinetic energy will be dissipated as heat. Same thing is happening.
In our analysis, we are not considering any.
At the moment, there is no viscosity or any dissipative force. These are.
Even then, there is as I come closer and closer to the horizon.
No. Wait. Listen to me very, very carefully. All I am saying is that the energy for a particle is given by this expression. This is the energy of the particle. There is no dissipation here. This is the energy of the particle. All I am saying is, okay, suppose I am interested in finding out the energy of the particle which is almost at rest. What is this energy? Almost at rest meaning what? That's what I did this calculation. I want to calculate for a particle which is almost at rest, what is dt by ds? ds is square root of g00 dx0 whole square plus g0i, etc. But a particle at rest, all the spatial component dxi is 0. Only term that will survive is this. So ds is square root of g0 is c square dt square. So ds is square root of g0 c dt. Put it here. The c dt will cancel and you will get the result that a particle at rest anywhere in the Schwarzschild black hole, it has energy this. Okay. So what is this? So E by C is this. So therefore E will be mc square into square root of this. So physically, any particle at rest at radial coordinate r, its energy is square root of minus 2gm by c square r mc. Then you see that you will ask that if r is Schwarzschild radius plus epsilon and epsilon tends to 0, this energy is 0. That's what this formula tells me. What physically it means is, I started with a particle from infinity and let it freely fall, and I keep on extracting its energy. So it comes near the horizon, because I am extracting energy. At horizon, I make it stall because I have extracted energy. When it is stalling, I know its energy is this. Epsilon going to 0, it's 0. It has gone to 0. But it started with energy mc square. So that means I have managed to extract mc square amount of energy by the time I reached the horizon. That's what. But extracting energy means I have used dissipative forces. Okay. All right. So I wanted to start cosmology early enough, but anyway, there is still time. So killing vector and point mechanics I have covered. But Karthik had asked a question that is there a global T mu semicolon nu equal to 0 as a local conservation of energy and momentum? Can you construct global conserved energy, global conserved momentum? In general, it's not true, but I'll show now if you have a killing vector, you can do it. Yeah. So, point particle trajectories are good enough for, compact objects like molecules, atoms, etc. But electromagnetic field is spread about. So therefore, you can ask, how can I talk about conserved quantity associated with electromagnetic waves, a scalar field, inflaton field? Those are fields. So what is the meaning of conserved? Is there a notion of conservation when you use killing vector? Answer is yes. It's very trivial, because we know that yesterday we talked about this. From Einstein equation itself, we find that there is local conservation of energy and moment potential, and I said that there is a mysterious thing, that you don't need equation of motion for the fields, but from Einstein equation itself you get the equation. So it requires more thoughts. How is gravity itself deciding the equation of motion for the fields? So this is something I have been always, I'm not the only person, many people have been mystified by this. Okay. Now, can we construct global conserved thing? By the way, I must tell you that in the case of electrodynamics, for every space-time geometry, the local conservation is current density J mu semicolon mu equal to 0, and from that you can construct globally conserved charge. That was in fact one of the problems I am sure Bhashwati would have. But in general, for matter, energy moment density, you can't do it when it's curved space-time. Okay? But supposing there is a killing vector. So again you say there exists a killing vector field for the space-time. Then you consider the following object, xi mu nu, xi nu. Call this something, call this q mu. Define q mu as T mu nu is xi nu. Okay? And ask yourself the following question, what is q mu semicolon mu? Q mu semicolon mu is T mu nu, xi nu, semicolon mu. Then you open up the bracket, you again see T mu nu, semicolon mu, xi nu, plus T mu nu, xi nu. But T mu nu semicolon mu is 0. Local conservation of energy momentum tensor. It's just mu and nu are being interchanged. Remember, energy momentum tensor is symmetric. T mu nu is same as T nu mu. So this tells me that this is 0. But T mu nu is symmetric, xi nu semicolon mu is antisymmetric, this is also 0. So we have the result that the quantity q mu semicolon mu is 0. But what is q mu semicolon mu? Q mu semicolon mu is partial derivative q mu comma mu plus, because the contravariant vector, plus gamma mu will be there, mu will be there, alpha will be there, q alpha. By now, you should be proficient in evaluating covariant derivative, and this, which is same as del q mu by del x mu plus gamma mu alpha mu, we know is del by del x mu of, yesterday we saw that, of log of root minus g. Okay, times q alpha. By the way, because alpha alpha is repeating, I may as well now call alpha as mu, because there is a mu mu. So I'll call it, or I will call this mu as alpha. It's all being summed over. So this object can be written as del q alpha by del x alpha plus 1 over root. The reason I decided to do this, normally in textbooks, you are not shown this. That part is shown, that p mu xi mu is a constant of motion. That part is shown, but for the energy momentum tensor, what I am doing is normally not given in textbooks. So that's why I decided that I must do it in the class. Q del q alpha del n 1 over square root of minus root g del root minus g by del x alpha q alpha. But then I can take 1 over root minus g overall common, and I have root minus g del q alpha by del x alpha plus del root minus g by del x alpha q alpha, that is equal to 1 over root minus g del by del x alpha of root minus g q alpha. But this is equal to 0. If this is equal to 0, this equal to 0 means I have got the equation that del by del x alpha of root minus g q alpha is 0. Now I can, this is a local equation, but from this I can construct a globally conserved quantity. How? Because note this quantity. Suppose I define capital Q to be this, root minus g q0 d cube x over space. Okay. Then you can immediately prove that capital Q is a conserved quantity, globally conserved quantity. Remember, the integral is over space. Capital Q is defined as root minus g q0 d cube x, meaning I am integrating over space. Why is it globally conserved? Take the derivative dq by dt, dq by dt. Then once it enters the integral sign, it will be partial derivative. So it will be del by del t of root minus g q0 d cube x. But root minus g from this equation is equivalent to 1 over c del by del t of root minus g q0 plus divergence of q vector. It is the same. I mean, divergence meaning not the, it's a curvilinear coordinate system. Strictly speaking, I should be writing summation I equal to 1 to 3 del by del xi of root minus g qi. That's what I mean. But xi's are in general not Cartesian. So correct way to write them. So therefore this object can be written as, okay, minus c root minus g qi summation I equal to del by del x. Summation I equal to 1 to 3 del by del xi of root minus g qi d cube x, integrated over entire volume. But use Gauss's theorem, it's a volume integral over the entire volume, and it's like divergence. When you use Gauss's theorem, it goes to minus g qi at the boundary. At the boundary goes to 0, and any physical quantities qi at the boundary must be 0. Or after all, what is qi? Qi is ti nu xi nu summed over. So energy moment tensor at infinity is 0. So therefore, by virtue of Gauss's theorem, this is 0. So I've just proved that this is globally conserved. So in other words, if your xi mu is a time-like killing vector, if your xi mu is 1, 0, 0, 0, then your object will be what? If it is 1, 0, 0, 0, then this object it can be written also as g mu g nu alpha or g nu alpha T mu nu xi alpha. If it is time like, only alpha equal to 0 component will you will have. So you will have g nu 0 T mu nu. That quantity, when you integrate over space into root minus g, is a conserved quantity. So only when you have killing vectors from T mu nu, you can construct globally conserved. Okay. It's not. So I will show it now. Good that you asked me, because now I am going to cosmology. So cosmology, we know that the universe is expanding and photons get redshifted. So photons that start from a distant galaxy, a blazar might be radiating gamma ray photons there. By the time you receive it, the photon energy is gone to lower values. That's the redshifting. I will derive all that. So therefore, energy is not conserved for particles, for fields. In an expanding universe, the energy is not conserved. So, there's a history. Harrison, who is a cosmologist, Harrison wrote a full book because of that question. So a student asked him that, isn't it funny that energy is not conserved in the expanding universe? So Harrison wrote a book. Will you be surprised? The answer is no, really. You should not be surprised that in an expanding universe, yes, particles like photons, etc., their energy is not conserved. But the energy is going in making the universe expand, because the potential energy is becoming, is more and more positive. Earlier, it was dense, potential energy was more negative. But then as it is expanding, potential energy is increasing. It must come out of the kinetic energy. So one shouldn't be surprised. Now let me go to cosmology, but yes, the fact that I did killing vectors, I must apply the killing vectors in cosmology. By the way, this is not done in any books, but some result is known. First let me tell you the result. It's done in a different fashion in cosmology book, but now that I have talked about killing vector, I will use a simpler method to state the result. You know that galaxies, so what we see are the galaxies. Some galaxies are field galaxies, meaning they are isolated galaxies. And many of the galaxies are in clusters of galaxies. There are rich clusters of galaxies called Abel clusters of galaxy. Coma cluster is one such rich cluster from which Zwicky talked about dark matter. So in clusters, the galaxies are moving very rapidly because they're bound system. And in a cluster of galaxies, galaxies can have as high random velocity as 15,000 kilometers per second. But field galaxies, isolated galaxies, they are almost cosmic observers. There are no peculiar velocity. So cosmologists ask, why is it so? Why are isolated galaxies not having peculiar velocity with respect to cosmic observers? Cosmic observers are observers for which r theta phi are constant. The answer is, that's what I am going to show, that you can show that even if you have a galaxy to begin with, it had a peculiar motion, as the universe expands, the peculiar motion will go down. And that is the same reason is why temperature goes down, because temperature is nothing but random motion. So what I am going to prove, same thing can be applied as to why does temperature of the universe go down as 1 over scale factor. What I'm going to I'll use the Killing vector to show that. Okay, now let me do by cosmology. What I mean is I'm going to now do FLRW model. FLRW is Friedman, Lemaitre, Robertson, Walker cosmology. So I have only 1 hour at my disposal. So whatever cosmology can be done in this, basic thing I want to point out, that's why I have worked out in details, whatever I have talked about in my set of lectures, they are well established. There is not even an iota of doubt. Okay. The rest of it is all, you do speculation and do lot of calculation, but you don't know whether they are correct. But whatever I have said, that's why I did detailed proof, they are established. There is not a single iota of doubt. Right. So, Robertson and Walker, two American general relativists, just like Schwarzschild. Schwarzschild was the first to show how to get exact solution in general relativity. So, Schwarzschild got an exact solution for a system which is spherically symmetric and time independent. That means static spherically symmetric solution. Carl Schwarzschild, he was fighting in the First World War and he was very badly injured. During that, as a battling soldier, he apparently got that's the story, I don't know whether the story is correct. He got first exact solution of general relativity and immediately sent it to Einstein. Einstein was very happy to see the solution and that led to black holes and all that. The next exact solution was by Robertson and Walker, who used the symmetry, again the Killing vectors. By the way, Killing vectors are the symmetry. Robertson Walker said that suppose I talk about space-time which is homogeneous and isotropic, meaning if I use a Killing vector corresponding to rotation, my metric should not change. If I go for quasi-translation, the metric should not change. And they established the space-time metric for homogeneous and isotropic space-time. And the metric that Robertson Walker established with their coordinates, the space-time line element is given by c square dt square. Then there is a function of time a square t r square. I'll call d omega square is a solid angle square. So normally it's written that way in a compact notation, where d omega square by definition is d theta square plus sine square theta d phi square. So that not always you should keep on writing this, it becomes very lengthy. So this is the Robertson Walker line element, and that's the reason r, t, theta, phi are called Robertson Walker coordinates. So any space-time that has 3 translational symmetry and 3 rotational symmetry, they will be of this form. Just like any spherical, a space-time which is static and has a spherical symmetry can be written as some function into dt square minus some function into dr square plus r square d omega square. That's how Schwarzschild started and got the Schwarzschild solution. Now Friedman one Russian general relativist, and independently, George Lemaitre, they got the dynamics. They said, okay, mathematically, this is a symmetry, but how can we realize it physically? They said that consider the cosmos. The cosmos probably at large scale is isotropic and homogeneous, but it's not at small scale. This is not a homogeneous space-time. Here we are clumpy objects, chairs are clumpy, tables are clumpy. You can't use this metric for this room. You can't even use this metric in space because Earth's gravity is not homogeneous. Okay? So therefore, this metric cannot be even applied to galaxy. Only on scales where the universe is homogeneous and isotropic, only then you can apply this metric. And therefore, this is applicable on scales greater than or equal to roughly 200 megaparsec. Remember, now we are doing cosmology, so we have to get our distance scales correct. What is 1 parsec? It is about 3.26 light years. In 3G CGS system, it is this. 1 kiloparsec is 10 to the power 3 parsec. 1 megaparsec is 10 to the power 6 parsec. Okay. So only on scales more than 200 megaparsec, the universe appears homogeneous and isotropic. But of course, is there a proof? The answer is yes. Radio astronomers have detected radio galaxies and radio quasars very far away. So hypothetically, if you take a 500 megaparsec cube and translate it and count the number of radio galaxies, then within Poissonian fluctuation, the number is same. So yes, on such large scale, the assumption that universe is homogeneous and isotropic is a good assumption, but people like Subir Sarkar would beg to differ. They have been for a very long time trying to show from observations that at least on scales of 500 megaparsec, there is large scale flow, there's large scale anisotropy. Anyway, the jury is still out whether Subir Sarkar's group is correct or whether Nobel Prize winner Brian Schmidt, their work is correct. We will soon, I mean, observations are the best arbiters. We should wait for James Webb Telescope results. Soon the things will be settled. But as of now, most astronomers believe that universe on scales bigger than 200 megaparsec, universe is indeed homogeneous and isotropic, and therefore we can use the Robertson-Walker metric and do dynamics. Assume matter is distributed on such scales in a homogeneous and isotropic fashion, and then if the matter is described by a perfect fluid, if T mu nu for a perfect fluid, the energy momentum tensor is and indeed the mass points, galaxies are, so for cosmologists, galaxies are like point particles. So they are randomly moving and their energy momentum tensor is, with a great approximation, can be described by a perfect fluid energy momentum tensor. Okay. Now you go, see, we are talking about r theta phi coordinate system. The physical significance of r theta phi coordinate system we have talked a lot in the past. Geodesics, r theta phi constant are geodesics, and not only that, observers for whom r theta phi are constant, the universe appears isotropic for them and homogeneous for them. While if your r theta phi is changing with time, then you will not see the universe to be isotropic and homogeneous. For example, Earth is actually moving with respect to cosmic observer, and that's the reason cosmic micro background radiation doesn't appear isotropic for Earth. There's a dipole anisotropic that Kobe, Planck, WMAP satellites have shown. All right, now you go to cosmic observers, then UIs will be 0, only U0 will survive and all that. You set up your Friedman-Robertson, put them in this metric and solve the Einstein equation. So you solve the Einstein equation, G mu nu. At the moment I am not bothered about cosmological constant. You can do that also. Put this T mu nu, solve the equations, you will find there are 2 equations you will get. Energy density, this energy density, and the other equation is twice second derivative, time derivative of the scale factor. A of t is called the scale factor, dot is a single derivative, double dot is second derivative. Where P is this pressure. Perfect fluid better be the description for the energy momentum tensor for the matter, because universe appears isotropic, and indeed for a perfect fluid pressure, when you are on a co-moving fluid element, pressure and energy density, they are isotropic. So they are internally consistent with each other. Right, there are these 2 equations. Someone will say, oh, very good, from the Einstein equation you have got this equation. But the fact that the perfect fluid itself should satisfy its own equation, and the own equation is what? T mu nu semicolon nu equals 0. This should give you also another equation, but it turns out that the equation is not independent of that. That equation can be written as, so this equation that follows is d by dA of energy density A cube plus 3 times pressure A square is 0. From this local conservation of energy and momentum tensor and using the perfect fluid in the Robertson-Walker space-time, you can find that from this you can derive this equation. This has a very nice thermodynamic interpretation. Towards the end, let me cover, then later on I'll tell you what's a simple thermodynamic thing about this equation. But you can show, it's a nice mathematical exercise, you can show by combining these 2 equations you can get back this equation. So in other words, the 3 equations are not independent. Only 2 out of these 3 equations are independent. I can combine, I should combine 2 equations. I'll tell you something very nice. Note that this part is common to this part, and therefore if I use this equation here, I get the result that twice A double dot by A plus 8 pi g by 3 energy density is minus 8 pi g pressure. And if I can take it to the other side, and I get the equation that A double dot by A is equal to, because there's 8 pi g factor, 2 factor, I can divide by 2, and therefore I get 4 pi factor, I get minus 4 pi g P plus 1/3 energy density. Okay. Which is same as minus 4 pi g by 3 energy density plus 3 times P. Okay? This immediately tells us a very deep result. It says us for standard matter that we know, including dark matter, what we know is pressure is always positive. If pressure is always positive, energy density is always positive. Because rest, even a particle at rest has rest energy mc square, which is positive. So that divide by volume, so therefore energy density is positive. Energy density for standard matter is always positive, and for all thermodynamic systems we know pressure is always positive, and therefore A double dot by A is negative. That means the expansion is such that A double dot is negative, and therefore you can only have decelerating expansion. That's what we expect. But there, independently, Brian Schmidt, Adam Rice, and Perlmutter, by looking at the type 1a supernovae explosions in different galaxies and plotting their apparent magnitude versus the redshift, they claimed that the acceleration, the scale factor which describe the cosmological expansion, its second derivative is negative. Of course, you should remember, I mean, whatever you conclude, you have to state the underlying assumption very carefully. This is true only if type 1a supernovae behave like standard candles. That means, yes, local, in the local universe, local galaxies, yes, indeed type 1a supernovae, after doing some normalization, it appears no matter where it is going off, they have the standard candle attribute. But how do you know distant galaxies, the chemical evolution, the chemical neighborhood is not contaminating your stars so that type 1a supernovae aren't behaving differently? It can happen. Then the conclusion would be wrong. So the underlying assumption is that type 1a supernovae indeed can be used as standard candle. With that underlying assumption, the three people's conclusion that the expansion of the universe is accelerated, that conclusion is correct. Then there is a problem. How can you reconcile your Friedman equations, Friedman-Lemaître equations with observation? Yes, there is an element of reconciliation, and that thing is, due to some reason, there is some exotic matter for which energy density plus 3, that means you take the entire matter, baryonic matter, that is what we are made of, dark matter, and plus add to it something crazy, which cosmologists called as dark energy, total it up, total up the energy density, total up the 3 pressure. If this combination is such that total energy density plus thrice total pressure is negative, yes, then you can have accelerated expansion, following from general relativity itself. So if in nature you have some exotic substance called dark energy, for which pressure is more negative, that minus 1/3 energy density, then indeed you can have accelerated expansion. It follows from Einstein's general relativity. You don't need any additional assumption. General relativity itself tells you that it is possible. Okay. All right. Now, let us do one derivation. Namely, given, you will say that, how do we know, how do energy densities of different substances evolve as the universe is expanding? How would dark energy evolve under expansion of the universe? So I'll give you a general proof of how they should. I'll use this equation to tell you, give me an equation of state, I will tell you how it changes with as the universe expands. So equation of state, when we learn thermodynamics, we are told that equation of state basically that which relates energy density or equivalently density with pressure. That's when you say equation of state. For example, when we were in school, we were told the ideal gas equation of state is PV equal to nRT or whatever, NKT, PV equal to NKT or something like that. So that is giving me an equation of state which says pressure is proportional to density and the proportionality has a temperature, okay? NKT. So N is like density and KT the proportionality constant. In general, in astrophysics and cosmology, we write our equation of state as pressure is some constant W into energy density. This W is called equation of state parameter. So let's take some particular example. Dust. If I take the perfect fluid dust, what is the equation of state? W is 0 because pressure is 0. Suppose I take a system of ultra-relativistic particles. What is the equation of state? W is 1 over 3 because for electromagnetic radiation, you can prove for electromagnetic radiation, if you have a gas of photons, the equation of state is exactly pressure is 1/3 energy density. You can prove it. You can just take the energy moment tensor of electromagnetic field and you can prove the equation of state is pressure is equal to 1/3 energy density. Okay? If this W parameter is a constant, then I will derive how the energy density evolves as the universe expands. I will give the proof for the case when W is a constant, any constant. Now let's see how you can prove the evolution. Just use this equation. So 0 is equal to d by dA of energy density AQ plus 3p, but p is W into energy density A square. By the way, yesterday Devabrata was doing some calculation. The whole thing can be also be written as some derivative of the energy density plus 3 Hubble parameter into all that. They are all equivalent because the Hubble parameter in cosmology, this quantity h of t called the Hubble parameter is defined as A dot by A. We'll see what its physical significance is. All right. So I have got that equation d by dA of energy density A cube is, so we have to integrate it. That's very simple because it says therefore d of energy density A cube is equal to minus 3W energy density minus 3W energy density A square dA. Okay. All right. And therefore, what I can do is, this is same as minus 3W energy density A cube dA by A. I just multiplied by 1A. Why did I do that? Because I want to integrate both sides, right? So, therefore, this can be written as dA cube by A cube is equal to minus And I have assumed W to be a constant. W is a constant. I'll integrate both sides. When I integrate both sides, I get log of Q is equal to log of, which is same as because log of x to the power n is n times log of x. That's the thing I have used. And hence, I get the result you exponential both. The e raised to power log of x is x itself. Exponentiate both, and you find the result that EA cube is equal to, proportional to some, so it's proportional because you can add a constant to it, so E is proportional to some constant k a raised to power minus 3. And hence, we have the result. This implies that energy density divide by a cube both sides, so some constant a raised to power minus, what is the result I get? So a raised to power minus 3 plus 3w, right? Is this the result I get? Yeah, something like this. So in other words, I can get it at k a raised to power minus 3 1 plus w. Okay, so energy density of any matter for which W is constant goes as this. So therefore, let's see what happens when W is 0 for dust. If W is 0 for dust, we find energy density goes as 1 over a cube. And dark matter particles, cold dark matter particles, their pressure is 0. So therefore, their density, energy density will go as 1 over a cube. The physical way also I can explain it. If there's a question, I'll explain. For radiation matter, W is 1/3. 1 plus 1/3 is what? 4/3. 4/3, 3. So for radiative, alternative particle, energy density goes as a raised to power minus 4. So dust, energy density proportional to 1 over a cube. For ultraviolet or radiation, goes as 1 over a to the power 4. Now you ask, can I have a system for which energy density is just constant? Pure constant. When can that happen? When W is minus 1. If W is minus 1, this is the case of cosmological constant. When W is minus 1. W equal to minus 1 means energy density is equal to minus pressure, or pressure is minus energy density. Then you find that. But why, I mean, should it be the case that for cosmological constant, energy density and pressure should be related minus 1? I told you, I can add to the Einstein equation this term g mu nu, and that's the equation with Einstein. But this quantity I could have taken to the energy momentum tensor side. So therefore I can say that cosmological constant energy momentum tensor T mu nu for lambda is this. Now you raise one of the index, so therefore this tells me that T mu nu for lambda is, I have raised one of the index, but what is G mu upstairs, nu downstairs, what is that? Kronecker delta. So this is therefore lambda Kronecker delta. Therefore, T00, which is the energy density, is lambda. Tii is lambda. But you know from perfect fluid, you can easily prove from perfect fluid, Tii corresponds to minus pressure. That's obvious from this equation, because for when a co-moving frame, II, co-moving, this is 0, it's minus P GII. So therefore, TII is minus pressure, and therefore you can see that because TII is lambda, so pressure is minus lambda, energy density is lambda. So equation of state parameter W is 1. And therefore, when W is 1, this is, you can see, energy density plus 3P for cosmological constant is negative. So cosmological constant, if it is there, it will drive an accelerated. But in general, of course, the dark energy group of cosmologists, in general, they take W to be more negative than minus 1/3. Then also you can have it. So that's the whole industry of dark energy models. Which model is correct? Matter of convenience, faith, your bullying nature, whatever. Okay. So, okay. But the fact of the matter is, observations keep on telling us W is close to 0.93. That's also another problem. Why should it be so close to -1? Why should dark energy models mimic cosmological? That's another problem. So let's not go into it. Yeah. What did I want to tell you more? I want to use the Killing vector analysis to show that temperature of the expanding universe keeps on falling as 1 over scale factor. Okay. Then I will show another thing, redshift. Why do photons get redshifted, and the redshift relation with expansion? Those also I will prove. But those are related with observations. I will prove it for a particular case, k equals 0. So this is your Friedman-Robertson-Walker line element. Suppose I take the case k equals 0. K equals 0 is called the flat space. So I'll k equals 0 case. It's sometimes called Einstein de Sitter universe, sometimes called flat model. So I'm considering k equals 0 model. K equals 0 model, our line element ds square, k is 0, so therefore this is simply dr square plus okay. This is a k equals 0 model. But you can see what are the Killing vectors. You can't obviously read the Killing vector from the following point of view, from the following coordinate, but I can always convert it to Cartesian coordinate system. So my Cartesian coordinate system is what? That x is r sine theta cos phi, y is r sine theta sine phi, and z is r cos theta. When I do that, the whole k equals 0 model can be written as c square dt square minus a square t dx square plus dy square plus dz square. Okay? All right? Now, You can immediately identify the killing vectors. What are the killing vectors? Because the metric doesn't depend upon x, y, z. Okay. So therefore the killing vectors are, there are three killing vectors, xi mu I, which can be written as, first component is 0, the others are, or I can write it more simply, del mu I, because when mu is 0, 0 I is spatial variable is 0. There are three killing vectors which can be. But then if this is so, then my P mu, remember P mu is by definition mc dx mu by ds. Okay. The 4 momentum associated in this curvilinear coordinate system, mc dx mu by ds. Okay. And we have already shown that the constant of motion, so P mu, xi mu is a constant of motion. So therefore, there should be 3 constants of motion for I equal to, so I is going from 1 to 3. Okay. So this is a constant of motion. That means as you move along geodesic, P mu, xi mu, I for I equal to 1 to 3 is a constant of motion. So therefore let's simplify. What are these constant of motion? So this is same as G mu nu P mu xi nu of I. But xi nu of I is delta nu of I, so this is equal to, so this is same as G mu nu P mu. The 3 killing vectors are delta nu of I. Delta nu. So nu is being summed over, so you get the result G mu I. So this is Kronecker delta, so only when nu is I is non-zero. Okay. But we know that Robertson-Walker line element is diagonal and therefore you get the result. So let me write it down. What are the constants of motion? The constants of motion are, let me call some symbol, Pi is GII. So let me put a minus sign because it will be negative. So let me put my definition minus script Pi by definition is this. So it is GII Pi because it's diagonal. GII Pi. And what is GII? GII is minus a square t. So therefore you get minus a square of t. So in other words, we see that a square of t, what is Pi? Pi is mc dxi by ds is a constant of motion because Pi is that, is a constant of motion. But we have to now interpret that these 3 components mc dxi by ds is a constant of motion. But physically, remember, xi is arbitrary curvilinear coordinate system. Interpretation, as I have always said, interpretation means you have to go to the local inertial frame system. Now look at the line element. If there is a line element and I want to make a correspondence with Minkowskian coordinate system, if I take a local coordinate Minkowskian coordinate system, what would it look like? It should be c square dt square minus d capital X whole square minus d capital dy whole square. So therefore, Minkowskian coordinate system, if I call it xi, is actually a of t xi. So d of xi is, and therefore the Minkowskian, the physical momentum, the actual physical momentum components are mc d capital Xi ds. So that this is mc, and the relation is mc a of t dxi. But this is what is the physical momentum components. Okay. What is constant of motion is this. That means what we have proved, all these, they prove what is constant motion, that a square t mc dxi by ds are constant. There are three constants, call it capital Ki. Each of them are constant. So therefore, physical momentum, however, is not this. Physical momentum is this. So what we have proved, physical momenta components, call them something. They are capital P I. They are the physical momentum, defined physical momentum. This is constant, meaning that physical momentum A into a t mc dxi are the physical momentum. So this implies that A of t into physical momentum pi are constants, where I is 1 to 3. So k1, k2, k3 are constant. So this immediately tells me physical momentum is ki by A of t. Okay. So what we have proved from Killing vector analysis is the physical momentum of particles moving in an expanding universe, the physical momentum go down as 1 over A of t. Okay. All right. I have proved it for k equals 0, but you can show for k equal to plus 1 minus 1 also this is true, but for that you have to use the geodesic equation. I am using the Killing vector so that I don't have to do an additional integration. I didn't do any calculus because Killing vector gives me a relation directly between first order derivative of coordinates, while geodesic equation is second order derivative of coordinates. So Killing vectors gives me a simpler way of showing that indeed the physical momenta components pi go down as the universe expands, as 1 over A of. Okay.
So in a contracting universe,
If in a
contracting universe.
good. So if the universe is contracting, physical momentum will go up. Correct. So a peculiar motion of a galaxy as the universe is contracting, peculiar velocities will keep on increasing. So we showed that any particle, the physical momentum components px, py, pz, the values will go down as 1 over scale factor. Now you ask about photons. For photons, pi magnitude is nothing but h nu by c, where photon having energy h nu the momentum magnitude is h nu by c. So h nu by c will also go down as 1 over scale of factor. That means nu, frequency of a photon, will go down as 1 over scale factor. So if you have a thermodynamic black body radiation, the frequency is going as down as 1 over a of t, and therefore the temperature must go as 1 over a of t. Okay. So that's the reason why the cosmic microwave background radiation, which is black body radiation, as the universe is expanding, the temperature of the cosmic background radiation is going down as 1 over scale factor. So today the cosmic background radiation has a temperature of 2.725 degrees Kelvin. At the time of decoupling, the temperature was 1100 degree Kelvin. So for photons, momenta goes as h nu by c, and therefore black body temperature, namely CMB, cosmic microwave background, black body temperature goes as 1 over a of t. But this is a general result, that any peculiar motion, if a galaxy had a peculiar motion, the momentum will go as 1 over a of t. So an isolated galaxy, as the universe is expanding, will slow down and come to rest. Okay. Now another observable parameter, namely, because what we deduce about our cosmos is by observing light that is being emanated from different cosmic sources. We cannot go out, we are limited by speed c. So all of our deduction regarding cosmos is by observing and interpreting radiation that is emanating from cosmic sources, and therefore we have to carefully interpret what we are seeing. So now I will talk about the redshift of radiation coming from distant sources. By the way, I had already talked about angular sizes of objects when we are talking about physical measurement and GR. So that is another observable system. Oh, I shouldn't have, doesn't matter. I can again go back and write down the Robertson-Walker line element. Redshift, cosmological redshift. There are Doppler redshift, Doppler blue shift, gravitational redshift, Pound-Ripka experiment, gravitational blue shift, but I am talking about cosmological redshift now. For a contracting universe, we will have cosmological blue shift. Okay. So imagine you have an external cosmic source, and here you are the observer, and light is coming from the cosmic source and reaching you here. This is light, radiation. So the cosmic source, let's say its Robertson-Walker coordinates are r1, θ1, phi1. Observer by definition is the origin, r is 0. Okay? All right? Now, all we see is rest mass particles coming from the cosmic source, call the source as S, and it's coming to me. And what is the interpretation? Yeah, let me write down the Robertson-Walker coordinates again here, because that should be, and for general k case. For a general k, there is 1 minus k r square. This is for k equals 0. This is my general Robertson-Walker line element. Okay. Now we will do what we measure. So again, there's an instance of how general relativity quantities, when we make measurement, what we mean by that. That's what we are going to do. We are going to talk about light traveling from the source to us. Obviously, light will follow null geodesic ds square equal to 0, because in local inertial frame ds square is 0, because light traveling with speed c, meaning c square dt square minus dr dot dr is 0, because it's, and if it is in local inertial frame, if for light ds square equal to 0, in any general coordinate system ds square must be 0, and therefore even in this cosmological background, the light as it is coming towards us will have ds square equal to 0. But now we are talking about null geodesic. If there's a source here and it is radiating, unless there's a gravitational lens, the radiation from the light will come straight radially towards me. Yes, if there's a massive object like a cluster of galaxy, there'll be gravitational lensing, bending of light and all. But if there's no gravitational lens intervening the cosmic source and observer, then the light, when it travels, will come only along a radial geodesic. That means this radial geodesic, theta 1 and theta phi, this theta 1 and it will be same theta 1 and phi 1. Only r will be changing and only time will be changing. So for this radial null geodesic, what will be the equation? D theta square is 0, d phi square is 0. So therefore ds square equal to 0 is c square dt square minus a square of t dr square minus divided by 1 minus kr square, because for a radial null geodesic theta phi are constant. Okay, so this part will be 0, and because it's null geodesic ds square is 0, so we have the equation c square dt square minus a of square a square t dr square, by that is 0. Okay. And therefore this sets up an equation which tells me that c dt is plus minus is equal to plus minus a of t dr by square root of 1 minus kr square. All I have done is I have taken this, the whole thing is 0, I have taken this to the right hand side and the equation is, and I have taken the square root. So strictly speaking, we have to be always mathematically accurate. When you take a square root, we must take both positive and negative root, and depending upon the physical situation, you choose which is the root. If the light ray is coming from the source to us, should I choose the positive root or the negative root? Here you have to use physics, because mathematics will tell you all possible. A photon coming from R1 towards 0, dr is negative. Okay? But tt, the time, remember what is the interpretation of the Robertson-Walker time? It is the proper time as measured in a local inertial frame or as measured by a co-moving observer. T is the real time, physical time. So tt is always positive, and the photon is traveling from higher R1 towards 0. So dr is negative. So therefore dt is positive, I have to take the negative root. So therefore, for me, for a photon coming from a distant cosmic source, so I will only choose the negative root. And therefore this tells me that the equation is c dt. I'll put all time dependent quantities on one side. C dt by a of t is minus dr by square root of 1 minus kr. All right? Now, light is a wave, so light is being emitted. It's a wave which is being emitted. So, first wave, let's take crest of the wave. It started, let's say, at time t1. Okay. Crest of the wave, one started at time t1. So, I'll integrate it now for the crest of the first wave. So, this is crest 1 which started earlier and next followed by crest 2. So, for 1, crest 1, the equation will be C integral dt a of t started at time t1, started at time t1 and reaches me at time t0. This must be equal to minus integral dr Where did it start from? It started at time t1, it started from r1. And where did it come? It came to the observer, which is at 0. That's why negative sign, everything is nice. I can invert and I'll get the positive sign. Minus r1 to 0 is same as plus 0 to r1 dr by square root of 1 minus x. Okay? So, I am talking about this crest 1 electromagnetic wave. I am talking about a monochromatic wave. The first crest started at time t1, it travelled along and reached me at time t0. Now, I will talk about crest 2. It started at what? T1 plus delta t1, because there is a delta t1 and this delta t1 is the real physical time as measured in the frame of the source. It is a physical time, that's the interpretation we have given for the, and it started at t1 plus delta t1, reached at time t0 plus delta t0 dt by a of t. And what is it equal to? It is minus, where did it start from? Well, the galaxy is at rest. It is a cosmic source and we have proved isolated galaxies won't have peculiar velocity. Peculiar velocities will go down as 1 over a of t. So, assuming that galaxy is at rest, it started from r1 only, its position has not changed. So, for those who want to apply what happens if the galaxy was moving with great velocity, you can't use this. You have to give that correction. And you will find that you will get the Doppler correction back. It's a nice physical exercise. If I were to write a cosmology book, I would put in that as a problem, that if the galaxy was moving, you will actually get back your Doppler shift in that. But the same as now you have got a fantastic solvable equation. What is the beautiful thing about the equation? The right hand side in both cases are identical.
Sir, I just want to ask
Yeah.
three questions.
Yeah.
So this T1 and T0 are observer time. Who is defining this
Ha,
T0?
No, no.
And what is dt again?
Robertson-Walker line element, this T is the proper time as measured.
Inertial frame.
That is true, but it is also true that cosmic observers, by definition, who are the cosmic observers? Those whose coordinates r, theta, phi don't change. Then ds square, c square, dt square is actual physical time. So the observer who is at rest galaxy at rest, what he is measuring as dt is a real physical time. I am also a cosmic observer. My galaxy is also not changing its position. Whatever I am measuring is also the physical time. So whatever we are measuring, whether it's delta t naught, delta t1, they are all physical time. Good clocks measuring the time. Because for r theta phi 0, these terms will not be there. ds square is c square dt square. And ds square by c square is the actual square of the physical time.
Correct. So basically, delta T naught is measured at observer position and delta.
No. So they are having good clocks, they measure time. We are now looking at the waves going from one end to another. Wave there emitted, the emitted wave, the crest 1 started at time t1, next crest 2 started at t1 plus delta t1. We are saying, when would they arrive at our place? That's we are asking. And we have got the equation that because the right hand sides are identical, we have got the equation that t1 delta t1, t0 delta t0 dt by a of t is same as t1 t0 dt by a of t. Because this part is same, we have got this equation. And it's very simple to find out the relation between delta t0 and delta t1. Why? Because delta t0 and delta t1, they are small quantities. We all know from our calculus days when we learned integration, we know that x to x plus delta x, any function f of x dx, when delta x is infinitesimally small compared to x, this is nothing but f of x delta x. That is what I am going to use now. And another factor is that if I have a quantity thing like x to y f of x dx minus y plus delta y x f of x dx, if you have this quantity, this is nothing but y to y plus delta y f of x dx. Because these are integral is like area, and when you have something to something and something, so when you subtract, you'll get this. All those things of basic integral calculus I will use. By virtue of the fact that these two are identical, I have got this equation, and hence therefore I have the result that this is same as this to this. I can write it as t1 plus delta t1 to t naught dt a of t. So this quantity, the LHS, this can be written as t naught to t naught plus delta t naught this, and finally the RHS. But t1 plus delta t1 to t naught dt by this can also be written as, this is same as t1 to t naught dt by a of t minus t1 to t1 plus delta t1. This piece is same as this, because this was this integral T1 to T0 can be written as T1 to T1 plus delta T1 plus T1 plus delta T1 to T0, and therefore I have to subtract this, and then plus but now the magic, this quantity and this quantity gets cancelled. So this cancels with this, and we have the result. What is the final result we have got? We have got the result that this is same as this, because there is a minus sign. We have got the result that T0 to T0 plus delta T0 dt by A of t is equal to T1 to T1 plus delta T1 dt by A of t. Okay. Well, there is a minus sign here. And I have already mentioned that x to x plus delta x fx dx is, when delta x is very small, is fx dx. So therefore this quantity is nothing but what? Delta T0 by A of T0 is equal to delta T1 by A of T1. We have got a fantastic result. So let's write down the result first, and then we'll do the physical interpretation. What is the result we have got? We have found that delta T0 by delta T1, delta T0 by delta T1 is equal to A of T0 by A of T. This is the equation we have got. Physical interpretation. Physical interpretation is that two light rays, first was emitted at T1, next one was emitted at T1 plus delta 1. That means the interval between the two light rays was delta T1. This interval, when it reached, I received the signal at T0 from the first light ray. The next light ray came at T0 plus delta T0, and the delta T0 by delta T1, this ratio is this. If the universe is expanding, A of T0 is bigger than A of T1. So therefore I will see that two light rays that was emitted from the source with a gap of delta T1, by the time it has reached, it's got stretched out. By how much amount? By A of T0 by A of T1. But the same thing, and two light rays, instead of two light rays, as I said, is the crest. Crest was emitted at 1, the next crest was emitted at 2. So if I multiply by C, the same as C delta T0 by C delta T1 is also equal to A of T0 by A of T1. But what is C into delta T0? If it is light crest wave, is the wavelength. Okay? Because if there is a period between, if the gap between two wave crest is delta t, C into delta t gives me the wavelength of the light. So therefore I have got the result that observed wavelength, because C into delta T0 is the observed wavelength, by emitted wavelength is equal to A of T0 by A of T. And for an expanding universe, A of T0 is bigger than A of T1, is expanding. A of T is increasing with time. And therefore, lambda observed by lambda emitted is this. And this is called the redshift, cosmological redshift. So I can remove this T1. So any light that is emitted at time t, so any light that is emitted at time t will undergo a redshift z of t and is given by A of T0 by A of t. So in other words, observed redshift, for example, that's what Hubble did. Hubble found that the distant galaxies, when you do the spectroscopic analysis, he could identify, after all, dominant gas dominant element in the universe is hydrogen. So he could see the Paschen lines, Balmer lines coming from the hydrogen. That pattern was there, but when he measured the wavelength did not match with the Paschen and Balmer lines with the laboratory wavelength. But when he multiplied by a factor, it exactly matched. He interpreted it as Doppler velocity. He said that galaxies are moving away, Doppler velocities. But that was, okay, I should not, okay, I'll say something more. I must end in 5 minutes, otherwise you guys will miss. So he interpreted as Doppler velocity and he got the Big Bang model. How? He said, how can we simply explain this result? That if galaxies were generated from a Big Bang, all moving with velocities, further away a galaxy today is, obviously for a long time it has, with a greater velocity it has moved. So he got the linear relation V proportional to the distance, and the proportional constant is today's Hubble parameter. But today we know that it is not Doppler velocity, it is actually cosmological redshift, and cosmological redshift is related to scale factor today divided by the scale factor at which light ray was emitted. Okay. All right. So redshift is something which you can measure spectroscopically. All you have to do is quasar or any other supernova type 1a, you measure the radiation, identify the line emission, and by comparing the spectroscopic line wavelength from laboratory measurement, you can immediately find out the redshift, and from luminosity distance, I don't have time to derive the luminosity distance, you can immediately obtain redshift is measurable. If you know what is the standard luminosity, you can compare it to the Hubble parameter and so on. That's the whole industry of observational cosmology. But because this was a GR refreshers course, I tried to say how observational parameters are coming from fundamental GR aspects of cosmology. I'll stop here. You can ask questions. So in other words, if you have a contracting universe, then you will see blue shift. In fact, late Professor Nardikar, Hoyle and Burbidge, they developed a quasi-steady state model where universe was locally oscillating and expanding. So his model predicted that you should see objects with blue shift because it is sometimes expanding, sometimes contracting. So it was a model which can be tested. Unfortunately, one has not seen blue shifted quasars. So with all present day observations, the standard model is a good model provided you assume dark matter exists and dark energy exists. Then the standard cosmology is the best model you have.
Everything takes into account the fact that the light is actually traveling out of a gravitational ray.
So yeah. So in one of our papers about fast radio bursts, we have estimated that how much redshift, gravitational redshift is a good point. You can find that, well, light is coming from accretion disk around a supermassive black hole. The light, when it's climbing the gravitational potential well of the, you'll find when you put in the numbers, those numbers are negligible compared to the cosmological redshift. Yeah, but yeah, you should, those numbers should also be put in. So you have to combine the gravitational redshift, which we did earlier, cosmological redshift, and also Doppler motion. What if the radiating object, remember accretion disk, matter is swirling around black holes, and matter which is very close to the event horizon, they are actually moving with speed close to the speed of light. So you have to also apply the Doppler correction. So people who do fitting of accretion disk, they include all these. In fact, a ion line, they get modified. A single ion line will develop double hump, because some are coming from the accretion disk. If the accretion disk is going like this, some are coming towards me, the other is going back. So Doppler blue shift, Doppler red shift, climbing out of the gravitational potential well, then cosmological redshift. So the observational part, you have to do all those corrections, and now people use all ready-made software these are all available. Then I lose interest. Now it's a black box. You just use the ready-made software and get the results. That is not interesting.